Unit 2, Atoms. This video will cover the Bohr model and modern atomic theory, as well as electron configurations and orbital notation. From the last chapter, you should have learned about atoms, parts of an atom, early atomic models, and isotopes. If you do not know what all of these words mean, you should go back and review that material before moving on to something new. The last atomic model you learned about was Ernest Rutherford's model. After completing the gold foil experiment, which was supposed to support the plum pudding model, Rutherford developed a new model for the atom. The Rutherford model had the positive charge of the atom located in a small central nucleus and surrounded by lots of empty space, and the electrons orbiting the nucleus in specific, unchanging, circular paths. This didn't explain some of the observations of atoms, such as their emission spectra. In other words, atoms, especially metals, were known to give off light of different colors when heated. It also didn't agree with Maxwell's theories in physics. According to physicists, an atom such as Rutherford proposed would implode in a matter of seconds. Clearly, more changes needed to be made to the model. Rutherford worked with one of his students, Niels Bohr, and a new model of the atom, the Bohr model, was developed. In the Bohr model, the positive charge is still in the nucleus, and the electrons exist in specific orbits around that nucleus. However, each orbit, or shell, has a specific amount of energy associated with it. The electrons can move from one shell to another by absorbing energy or emitting energy. The amount of energy absorbed or emitted, a quantum, plural quanta, determines how far an electron can jump. Atoms will only absorb or emit the amounts of energy associated with their possible quanta. This model was widely accepted, but further work by another physicist, Erwin Schrödinger, famous for his thought experiment with the quantum cat, led to the development of the quantum mechanical model. In this model, the electrons do not have prescribed orbits, but instead exist in a cloud around the nucleus. Within this cloud, the electrons can be described in terms of the probability of finding them within particular areas. Areas of high probability are called orbitals and are arranged in specific ways to form sublevels. Electrons still have the ability to jump from one level to another by absorbing or emitting quanta of energy. This is a timeline of the major atomic models and theories. Take a minute to look at this and see if you can identify the changes or major features of each model. If not, you may want to go back and study this. Let's move on to orbitals and electron configuration. As mentioned earlier, orbitals are the regions around an atom that describe the highest probability of finding an electron. Energy levels are numbered, called the quantum number, and each can hold a specific number of electrons. Each level has one or more sublevels, which are represented by letters S, P, D, F, G, H, etc. We're going to focus on S, P, D, and F. Each sublevel has one or more orbitals, and each orbital can hold 2 electrons. The first energy level, quantum number 1, has only one sublevel, S. The second energy level has 2, S and P. The third 3, S, P, D, and so on. Each sublevel has a different shape and different number of orbitals and can hold a specific number of electrons. Here is an example of how many electrons each individual sublevel can hold. S can hold 2, P can hold 6, D can hold 10, and F 14. They can do this because of the different numbers of orbitals they have. This is what the different sublevels look like. To figure out the electron configuration of an atom, or where the electrons are in that atom, we need to use 3 rules. The first rule is the Aufbau principle. According to the Aufbau principle, as an atom gains electrons, the sublevels are filled in order of increasing energy. This means the S level fills first, then P, then D, then F, and so on for each energy level. Next is the Pauli exclusion principle. This principle states that each orbital can only hold 2 electrons, and those electrons will have opposite spins. When drawing an orbital diagram, the electrons are represented by arrows, and their orientation, up or down, represents the spin. More on this in a minute. The third principle is Hund's rule. This rule states that when a sublevel is filled, the atom will first fill electrons of the same spin, 1 per orbital, then go back and add an electron of opposite spin to each orbital, instead of adding in pairs. When determining electron configuration, we can simplify the order in which the sublevels will be filled by using the diagonal rule. If the energy levels, 1 through 7, are written down one side of a table, and the sublevels, S, P, D, and F, are written across the top of the table, we can fill in each sublevel as shown. To determine the order of fill, we read across the table in diagonals, from the top right to the bottom left, as shown by the small arrows. This leads to the order shown at the bottom of the diagram: 1S, 2S, 2P, 3S, 4S, 3D, etc. It is also important to consider the number of electrons that can go on each shell. Remember that each sublevel has a certain maximum number of electrons, so we can add those up for each energy level. Level 1 can hold only 2 electrons, while Level 2 can hold 2 in S and 6 in P for a total of 8. The maximum number of electrons for any energy level can be determined by using the equation 2n squared, where n is the quantum number. By putting all of this information together, we can write the electron configuration for an atom. For example, potassium. Potassium has an atomic number of 19. So a neutral atom will have both 19 protons and 19 electrons. Using the order from the previous diagram and the maximum number of electrons per sublevel, we can write the electron configuration for potassium as shown. There is a shorthand method for writing out the electron configuration. As you can see from the example, large atoms will have very long electron configurations. To make it easy, you simply count backwards on the periodic table and find the previous noble gas, then write that element's chemical symbol. Then draw the electron configuration for the electrons beyond the number for the noble gas. For example, sodium could be written as neon 3s1. The other way to write electron configurations is by using orbital notation. In orbital notation, the orbitals for each level and sublevel are represented by circles or squares, as shown. Next, each electron is drawn in, following the rules already described. An upspin arrow is drawn pointing up, while a downspin arrow is drawn pointing down, as shown in the first orbital. Pause the video and try writing the orbital notation for potassium using the rules, then press play to check your answer. While most atoms follow these rules, there are a few that do not. Copper, for example, has a filled 3D shell, although this method would predict that it does not. The examples are mostly metals, whose altered electron configuration is more stable. Let's review. In this video, you should have learned about the Bohr and quantum models of the atom, quantum number, energy levels, and sublevels, the rules for writing electron configurations in orbital notation, as well as exceptions to those rules, and how to write configurations in shorthand.